Good morning, it's Jeremy. It's Friday, October the 14th, and today I want to talk about HF messaging with OFDM. Recently, I was in Costa Rica for my vacation, and I was lying on the beach under a palm tree, having a good time. I was catching up on my technical reading, and I came across an article in QST magazine about Vara, and I wasn't too familiar with Vara, so I looked into it, and it turns out that it's part of the WinLink. WinLink is a digital email service for amateur radio operators, and it's a modulation scheme that you can use. And it was developed by EA5HVK, Jose Alberto Nieto, and it's a pretty amazing program. So I thought I'd get into that. 2 years ago, I wrote an article or a blog post about using OFDM for SSB. And in that article, I talked about the orthogonality of OFDM, where you space their carriers, the multiple carriers at the baud rate. And I created an 8-channel model. There's the 8-channel model with 8 separate modulators. Now, you wouldn't do this nowadays. You'd build it using the IFFT or IDFT, and we'll talk about that in a minute. That's the model I came up with just to show how it worked to myself. And then individually in these blocks I chose a 16 QAM modulator, so each one of these blocks is a 16 QAM modulator, and that's the output spectrum. It's designed to go on an SSB transceiver bandwidth USB, so that'd be 300 hertz there, that's 2700 hertz, so you've got 2400 hertz there of bandwidth. Turns out with OFDM you've got a peak to average power ratio which is pretty high. That's one of the drawbacks here. You can see the signals fluctuating up and down. That's the receiver. The receiver basically takes, in this case, this was channel 2. So it was at 750 hertz. So that's the carrier reinserted for channel 2, and then you do a match filter, and it pulls out the data because all the other channels are orthogonal. And then I said, okay, I looked at some of the requirements for HF propagation. And we want to adjust the baud rate such that we can overcome multipath fading. So I came up with some numbers there. And then I built a more practical system in GNU radio. I built 128 channels there for voice. So that was something I looked at a couple of years ago. So in this particular post, I review for instance, the SSB bandwidth, and Shannon's law says that you can have a maximum capacity depending on your signal-to-noise ratio. So let's say we had a signal-to-noise ratio of 10, then we could only get about 8.3 kilobits per second. Then there's my 8-channel model. I looked at that again. That's the receiver. That's the I and Q data sent on channel 2, and that's the I and Q data received on channel 2. That's the integration there for the match filter receiver. And you can see that all the other channels are orthogonal, so they don't contribute to that, so you can recover your data. That's a picture of the spectrum on channel 8. That's the overall spectrum. That's the pulse to power to average ratio there. That's what it sounds like. Those were the channel specs. Bandwidth 2400 hertz, 8 channels. The input bit rate was 9600 bits per second coming into the channel. Divide that by 8, you get 1200 bits per second per channel. We're using 4 bits per baud. It's 16 QAM, so the baud rate was 300 baud. Those are my carrier spacings. And for OFDM, for orthogonality, you want these carriers spaced at 300 baud. Those were the specs. There's a little bit on HF propagation again. So here what I'm doing is I'm coming up with a theoretical OFDM messaging model here. When we look at the Vara, in later posts, when we look at the Vara modem, we're going to see that I think it has 52 channels. So if I had 9600 BPS coming in and I had 64 channels, which is more practical than 8, 8 wouldn't do the job. So 64 channels, that would mean a channel data rate of 150 bits per second, and if I choose, let's say QPSK, that works out to 37.5 baud or 26.7 milliseconds, which is the type of symbol time that you need to overcome the multipath fading. Now there's two great references I looked into. That's a block diagram of the first reference there. So instead of using individual channel modulators, what you do is you take your data, you break it up into, from a serial to parallel converter, you break it down into the N channels. And then what you do is you do an IFFT. We add a cyclic prefix, which we'll talk about in a later post, to overcome intersymbol interference. And then you D to A that, you do the conversion, the IFFT conversion. And then you D to A the real and imaginary samples and put them out into the channel. That's kind of the idea there. And that's just basically how you derive the IDFT or IFFT from the data. And that's talked about in detail in this particular reference here. And then what I did is I said, okay, I built an 8-channel model using discrete modulators. Let's see if I can build an IDFT to DFT simulator. I'll use the same 8-channel system, and I just want to see how it's built using the DSP because I hadn't done that before. So basically in my Psychos model here, I'm taking 9600 bits per second in. I'm splitting them up into 8 channels of 1200 bits per second per channel. I'm using 16 QAM like I did before, so it's 300 baud. And then what I'm doing is I'm collecting the I and the Q samples from each one of these channels to form a vector big capital XK. And that vector goes into an IDFT, giving me a small xn, real and complex. And that I'm splitting up into a real and an imaginary stream, going into a D to A converter. And I just have one modulator. Instead of 8 modulators, now I just have one. And I choose that to be the center of the bandwidth. So it goes from 300 to 2400. So the center is 1500. So there's my carrier. So that's basically my Psychos model. There's my 16 QAM constellation. It's not gray coded. So that's the input 4-bit patterns, and those are the I and the Q samples. That's I and the Q. So for instance, in channel 2, the second symbol, I think, was -1, so that represented 5 or 0101. There's the constellation for the 16 QAM. This is my IDFT code. So those are my 8 channels of I and Q data. I think I took the second from the PRBS generators. I had 8 of them. So I took the second symbol for each one of them, and that's the I and the Q data. So I took that, went into the IDFT transform to get XN, and I did the reverse transform to see if I could get the original symbols back, and that worked, so that's good. And then I split this up into real and imaginary parts. Okay, so that's the real part of XN, that's the imaginary part of XN. And then I created a stream where the real come in, and that's the imaginary. They're converted to they're converted from D to A, and then they multiply the cosine and the sine at 1500 hertz, and that's my output. So let's just quickly look at the model here. So in Psychos Lab, I build the data. So there's my constellation. There's my I and Q data from the 8 channels there. There's my IDFT. What I'm doing here is I'm padding the data out so I can get a spectrum in the Psychos model. I need more data because I'm only taking a look at the second symbol. So what I'm doing is I'm just repeating the data 5 times. And then I'm creating a structure and I'm reading that into Psychos. So let's run this. So there's my small xn real, small xn complex. I can look at, there's my constellation. There's my X capital XK is my I and Q data from the 8 channels. And there's my XN, whoops, it's XN. So that's the XN from the IDFT. Let's go to my Psychos model. So basically here, there's the real part of XN coming in. There's the imaginary part. So when I run this, So there's the real part of XM coming in. I've repeated it 5 times so I get enough data for the spectrum analyzer. That's the imaginary part. That's the real part times cosine. That's the imaginary part times sine. When you add them together, that's the output, and that's the spectrum. So if we look at the spectrum, and I just blow it up at the lower end here, you can see that basically there's from 300 to 2700, there's our output. So basically then, just to recap what I've done here in this particular blog post, is I'm looking at OFDM for messaging, and what I'm doing is I'm using, instead of using a discrete model, which I built before, I'm using a Psychos model with IDFT or IFFT to build my OFDM. So in the next post, what we're going to look at is the other things that we need to consider, for instance, for messaging, and that would be, let's say, forward error correction, error detection, cyclic prefix, etc. And then we'll look at the Vera software.